Well, this was a bit of a difficult problem, so let's try to work it out. We're given this satellite, and it's at the surface of the Earth, and we want to know what's the energy required to lift it until it's equal to the kinetic energy that it would be required to orbit this planet. So what it's really asking is, what is the change of potential energy from here, U initial, to U final? This is delta U. And when is it equal to the kinetic energy that is in orbit, 1/2 mv squared? When is that equal? Okay, that's really what it's asking here. So we have to figure out when is 1/2 mv squared equal to UF minus UO. And of course, we're going to know that, UF, actually let's start with UO. UO is equal to GMM over the radius of the Earth here. This is the mass of the Earth. And UF is equal to GMME. And then we're going to try to figure out what is this entire distance, H plus RE. There we go. These are actually negative values because it is potential energy. And then also on this side, we're going to be noting that V for something in orbit, it's B is GM divided by R. And again, what is R at that point? It's RE plus H. So it turns out that V in orbit for this particular planet would be GM over RE plus H. And we can plug that in for the value in our kinetic energy. Okay, so now we've got 1/2 m, and then that squared is GM divided by RE plus H is going to be equal to the negative GM ME over H plus RE, and then it's minus the negative, which is positive, GM ME over RE. And now, we'll note that a whole bunch of this stuff cancels. This is the mass of the Earth as well. This G's, all that cancels out. We're going to end up with 1/2 1RE plus H is equal to, well, I could say 1 over RE minus 1 over H plus RE. And if I move this to the other side, 1 over 2, 1 over RE plus H. Let's just go ahead and do something like that. Combine this. Just multiplying that together. Then we're going to add 1 over RE plus H. And then that's going to equal 1 over RE. And you'll note that if we just multiply this by 2, then it'll be actually 3 over 2 RE plus H. That's equal to 1 over RE. And this is good. We can now cross multiply. We're going to get 3, we'll do it over here, 3 RE equals 2 RE plus 2H. And that means that, well, it turns out that RE is actually equal to 2H. So 0.5 R is equal to H. Well, that's great. Now we can figure out that H, if we were to plug in, what's RE again? The radius of the Earth is 6.37 e to the 6 meters. If we divide that by 2, a little calculator over here, 6.37 e to the 6, divide that by 2, we get this interesting number. 3,185,000 meters. Okay, that is actually the answer for A. That is the height that is required. It was asking for the height, not the energy required. It was asking for the height where the energy required to lift. But yeah, so we were solving for height, not energy, for part A. So that's kind of nice. Now, it's asking for B here. At greater heights, is delta U or KE greater? For this, I was going to go back to the original equation that we had over here, just after we canceled everything out. And I wanted to do a little bit of tests and just see, okay, so if I were to do 1 over, 2RE plus 2H, actually here, let me keep that in 2RE plus H. If that were equal to 1 over RE minus 1 over H plus RE, this is the one I want to look at right now. And let's say that H at this particular point was 4 million, I guess, 4 million meters. That's 3 million. This is 4 million. All right. So we're looking at 4 millimeters. That's going to be plugged in for H there. And I'm going to set up a little inequality here. It's not equal. I'm going to figure out whether it's greater than or equal, because the question is really asking which one's greater. Is delta U greater or is KE greater? In this case, this is delta U, and this is actually KE. So we're going to try to figure out which one's greater, KE or delta U, at the H of 4 million. That's going to be greater than this. So we'll plug that into this, and we get 1 over 2 times, well, what is 6.37, that's the radius of the Earth, plus 4 million. What is that? That's just this. And 1 divided by 2 times that answer. I'll actually put it like this here. So 1 divided by 2 times that answer is 1 over that. Well, that's gonna be the same thing as saying 4.82 e to the negative 8 for KE, and then we're going to put a little box there. And then what is the delta U? It would be 1 over the radius of the Earth, which is 6.37 e to the 6, and then it's minus 1, and then we're going to add 6.37 e to the 6 plus our new, this is actually 4 e to the 6th plus 4 e to the 6th. And that's going to give us this number, which is the same thing as saying 6.055 e to the negative 8. And if we were to rewrite this into decimal form, that's actually 0.00000, I guess there's 7 zeros, and then a 4, 8, and then we're wondering if that's greater than or equal to 0.000000. That's 7 zeros, and then 6. Well, which one's greater? Turns out that the potential energy is actually greater than the kinetic energy. So it requires more energy to lift the satellite at the greater energies than it does to send it in orbit. Very interesting problem. Hopefully that was informative.